Here we have section 3.5, which is talking about multiplication and division algorithms, mental computation again, and estimation. So just like in the last section, there are a lot of things in here that I don't necessarily think are so important, and so we're going to kind of skip over those. They talk about estimating. They make a big thing about estimating again. And so, just like I said with addition and subtraction, you have to be very careful when you ask students to estimate an answer. Because if you are not specific about what place value you want them to round it to first, then they could give you very different answers and it would still be a good estimation. It may not be the estimation that the book wants them to get, but it would still be a good estimation. So you have to be very careful with that. Okay, also, I know that in the last section we did addition and subtraction of different base systems, and I think that was a very good exercise so that we could really focus in on what's going on with the borrowing and the carrying and all of that business. I would like to go through multiplication in different base systems, but I, I looked and looked and looked and I couldn't find anything that only had multiplication of base systems. They always had multiplication and division together. And division is a little bit more complicated, and I just don't think that it would serve the purposes to be helpful to you guys so that it would help. I don't think that it would help you to have a deeper understanding of what it is that you're going to be teaching with regular division. So we're going to go ahead and skip over that. Now, what we are going to focus in on in this section is exponents because they talk about exponent rules, and these are things that you do need to know. If nothing else, they're going to be on your teaching exams and stuff also, so you'll have to know that. The first of all, they talk about the definition of an exponent, and in your notation here also, this is worth noting that the this a here is called the base, and the n here is called the exponent or the power. Exponent or power. So it's important to have that vocabulary. Okay, so anything raised to a power, what that represents is multiplying that base to itself however many times the exponent says. So for instance, if I had something like said 2 to the third, that means we're going to take this base of 2 and we're going to multiply it to itself 3 times. It doesn't mean 2 times 3, it means 2 times 2 times 2, which is 8. That's a whole different thing. So this is the meaning of exponents. Now there are some rules, and I want to kind of show you why the rules are the way they are. Let's say that we had something like, let's say 2 to the fifth times 2 to the third. Well, let's just think about what that means. 2 to the fifth, it means 2 times 2 times 2 times 2 times 2, written out 5 times. 2 cubed means 2 times 2 times 2. So if we're multiplying those together, we're really just multiplying a series of 2's together. And how many times are we doing that? 1, 2, 3, 4, 5, 6, 7, 8. So 2 to the 8th. So a long time ago, they did this, many, many, many times and discovered that pattern that anytime you're multiplying like bases, all you have to do is add the exponents. And that's what this rule says. When you're multiplying like bases, you add the exponents. Okay. All right, now another rule that we have, which again is another shortcut, is what's kind of referred to as a power rule. Let's say, just for grins and giggles, that we had 2 to the fourth raised to the third power. Okay, well, let's think about what that means. The third power means we're going to be multiplying it to itself 3 times. So that would be 2 to the 4th times 2 to the 4th times 2 to the 4th. If we take 2 to the 4th and just look at it, doesn't that mean to multiply the base to itself 4 times? So that would be 2 times 2 times 2 times 2. And this 2 to the 4th would be the same thing. 2 times 2 times 2 times 2. And this 2 to the 4th would be the same thing. 2 times 2 times 2 times 2. And we are multiplying those together. So really we're just multiplying again a series of bases together. So that base is 2. And we're multiplying it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. Well, wouldn't it have been easier just to multiply 3 times 4 and get 12? That's exactly what this rule says. It says anytime that you've got a base to a power raised to a power, you multiply those powers. So that's a shortcut rule. Okay, our next rule talks about multiplying different bases but to the same power, and generally you see this one backwards, where this right side is generally listed first and then the left side is listed second, because it's almost as if you are distributing the power throughout the parentheses. So it would be like saying, now, but just to see if this is a true statement or not, let's see. If, let's call A 2, and N would be, oh, I don't know, 2 also. B, let's call 3, and N has to be 2 again, because those exponents have to be the same. So according to this rule, that would be the same thing as saying 2 times 3 squared. So let's just see if it's true. 2 squared would be 4, because 2 times 2 is 4, times 3 squared is 9, because 3 times 3 is 9, and 4 times 9 is 36. Okay, over here, we'd have to do what's in the parentheses first. So 2 times 3 would be 6, and we would have to square that. So 6 squared is 36, so that rule checks. Those are equal. But like I said, generally whenever you're working with this, you'll see it more in this form, and you'll have to distribute the power to the factors. Okay, our next rule is talking about division. And if you'll remember, division is just a fancier way, or an alternative, I'm not sure fancy is the right word, for a fraction, or a fraction is a fancier way of writing a division problem, however you want to think about it. So I could rewrite this as a to the m over a to the n equals a to the m minus n. Those would be the exact same thing. So let's test it out. What if I had 2 to the 5th over 2 squared? Let's see what that really means. 2 to the 5th would be 2 times 2 times 2 times 2 times 2. 5 times. 2 squared would be 2 times 2. True? And anytime you have something over itself, it's as if, I mean, a lot of times we say that they cancel out, but that's not exactly true. I mean, 2 divided by 2 is 1. So that's a big 1. This is a big 1. And what do we have left? We have 2 to the 3rd power. So wouldn't it have been easier, especially if these numbers were large? I wouldn't want to write out all of those 2's and then start doing your groups of 1 there. So if you had something large especially, it's much handier to know the rule. So when you are dividing like bases, you subtract the exponents. So 5 minus 2 is 3. There you go. And then finally we have the rule that says anything to the 0 power equals 1. Anything. So, and that directly comes back from the rule that we just talked about here, because anything over itself is 1. So let's say that we had something like 2 squared divided by 2 squared. Well, you could look at it a couple of different ways. You could either look at it the long, old-fashioned way, which would be 2 squared is 2 times 2, divided by 2 squared would be, again, 2 times 2, and then each one of these would be a 1, so you're just left with 1. Or you could even put them together and say 2 squared over 2 squared, anything divided by itself is 1. Or you could look at it as, when we're dividing like bases, we subtract the exponents. So if I said 2 to the 2 minus 2 power, that would be the same thing as saying 2 to the 0, which we've already shown is 1.